Hello and welcome. I'm so grateful you're here. As we begin, I'd love it if you'd share in the comments where you're joining from and what time it is for you. It always amazes me to see how people connect from every corner of the world, morning or night. Thank you kindly to those who've subscribed and pressed that little like button. It really does help. And if you ever have requests or themes you'd like me to explore, please share them in the comments. Now, let's get started. Chapter 1. Understanding Solar Flares, an Overview. Solar flares are magnificent, explosive bursts of energy emanating from the sun, captivating scientists and stargazers alike. Defined as a sudden brightening of a small region on the sun, these flares release an immense amount of energy, equivalent to millions of hydrogen bombs detonating simultaneously. They are characterized by their intense light and radiation, which can be observed across various wavelengths, from radio waves to X-rays. Imagine standing on Earth, witnessing the sun's surface erupting with dazzling brilliance, as if the sun itself were illustrating an intricate story of cosmic power. These events can last from minutes to hours, and their impact can reach far beyond the sun. The energy emitted during a solar flare can affect satellites, communications, and even power grids on Earth. Historically, solar flares have been observed since the early days of astronomy. One of the first recorded observations occurred in the mid-19th century, when astronomers noted an increase in solar activity coinciding with the appearance of sunspots. As technology advanced, the study of flares progressed remarkably. In the early 20th century, the advent of radio astronomy allowed scientists to detect the radio waves emitted by these flares, revealing a whole new layer of their complexity. One notable figure in the history of solar flare research is the astronomer George Ellery Hale, who played a pivotal role in studying solar phenomena. Hale's dedication to observing sunspots and solar activity laid the foundation for understanding the sun's magnetic fields and their connection to solar flares. In Hale's words, "The sun is a star, and it is a star that gives us the light and warmth necessary for life." This passion for understanding our closest star has inspired generations of scientists to delve deeper into the mysteries of solar activity. Solar flares are classified based on their intensity levels, which helps scientists communicate the potential impact of these events. The classification system includes several categories, such as A, B, C, M, and X, with each letter representing a different range of energy output. The X-class flares are the most powerful, capable of releasing energy that can disrupt communications and pose risks to satellites orbiting our planet. Imagine the sun's surface like a vibrant tapestry, woven with threads of energy and magnetic forces. The intricate interactions between these forces lead to the formation of solar flares, where magnetic field lines snap and reconnect, unleashing energy in a spectacular display. As we classify these flares, we gain insight into the sun's behavior and its potential effects on Earth. The study of solar flares is not merely an academic pursuit. It has profound implications for our daily lives. Understanding these energetic events can help us protect our technology and infrastructure from solar storms. For instance, when a significant solar flare occurs, it can produce a coronal mass ejection, sending charged particles hurtling towards Earth. These particles can ignite beautiful auroras in the polar regions, but they can also interfere with GPS systems and lead to power outages. Astrophysicists and solar physicists dedicate their careers to studying these phenomena, employing sophisticated tools and instruments to monitor solar activity. The Solar Dynamics Observatory, for instance, captures high-resolution images of the sun, allowing scientists to observe flares and other solar events in real time. This level of observation has ushered in a new era of understanding, revealing the sun's behavior with unprecedented detail. Consider the solar cycle, an approximately 11-year period during which the sun's activity waxes and wanes. During the peak of this cycle, solar flares become more frequent and intense, providing a rich opportunity for researchers to study their characteristics. The correlation between solar activity and the solar cycle brings a dynamic aspect to the study of solar flares, emphasizing the need for continuous observation and research. The implications extend beyond Earth. Solar flares can influence other celestial bodies within our solar system. For example, the flares can affect the atmospheres of planets like Mars, stripping away their protective layers and altering their climates over time. This interplay between solar activity and planetary atmospheres opens up fascinating avenues for exploration and understanding of our solar system's history. While we often think of solar flares as isolated events, they are part of a larger system of solar activity, including sunspots, solar prominences, and coronal holes. Each of these phenomena plays a role in the sun's overall behavior, and studying them collectively can enhance our understanding of solar flares. The importance of solar flares in astronomy cannot be understated. They serve as a reminder of the sun's dynamic nature and its influence on our planet. Observing and understanding these phenomena allows scientists to unveil the intricate processes at work within our nearest star. The knowledge gained from studying solar flares can also inform our understanding of other stars in the universe, shedding light on their behavior and the potential for similar phenomena elsewhere. As we ponder the vastness of the cosmos and our place within it, we realize that the sun, with its solar flares, is a vital piece of the puzzle. The ongoing research into these powerful bursts of energy continues to reveal the complexities of solar physics, encouraging curiosity and wonder about our universe. In the words of the renowned physicist Carl Sagan, the cosmos is all that is, or ever was, or ever will be. Each solar flare contributes to this cosmic narrative, reminding us of the interconnectedness of all things. As we continue to explore and understand the sun's behavior, we are not only learning about our own star, but also gaining insights into the broader mysteries of the universe. Listening to the whispers of the sun and its explosive energy can inspire a sense of awe and tranquility. While solar flares may seem distant, their effects ripple through time and space, influencing everything from technology to our understanding of life beyond Earth. The journey through the science of solar flares is one of discovery, patience, and wonder, as we seek to understand the forces that shape our existence in this beautiful cosmos. In this quest for knowledge, we find ourselves drawn closer to the sun, the life-giving star that illuminates our days and paints our skies. Each flare is a reminder of the power and beauty that lies within the universe, urging us to keep exploring, questioning, and marveling at the wonders that surround us. The classification of solar flares into distinct categories allows scientists to not only communicate about these events, but also to predict their potential impacts on Earth and beyond. Each type of flare, from the relatively minor A-class to the formidable X-class, tells a story of solar activity and magnetic field interactions. Imagine the sun as a grand symphony, where each flare plays a note that contributes to a greater cosmic melody. As we observe these events, we can begin to appreciate the delicate balance of forces that govern the sun's behavior. At the heart of this interplay lies the sun's magnetic field, a complex web of invisible lines that shape solar activity. These magnetic fields are not static. They twist and turn, sometimes building up tension that ultimately leads to a solar flare. The energy released in these moments can be likened to a tightly coiled spring suddenly released, sending shock waves that ripple through the solar system. The study of solar flares also reveals fascinating connections to the broader realm of astrophysics. For instance, the mechanisms behind solar flares are not unique to our sun. Other stars exhibit similar behaviors, and understanding our sun helps astronomers draw parallels with distant celestial bodies. This exploration raises intriguing questions. How do solar flares on other stars compare to those of our sun? What insights can we gain from their patterns and behaviors? To deepen our understanding, scientists utilize various observational tools and methods. Space-based observatories, such as the Solar and Heliospheric Observatory, continuously monitor the sun, capturing high-resolution images that reveal the intricacies of solar flares. These technological advancements have opened new doors for research, allowing scientists to study the life cycle of a flare, from its initial formation to its eventual dissipation. One remarkable aspect of solar flares is their unpredictable nature. Despite our growing knowledge, accurately forecasting when and where a flare will occur remains a challenge. The sun operates on a scale of complexity that often defies our attempts at precise prediction. This unpredictability adds an element of excitement to solar research, akin to standing at the edge of a vast ocean, where one can only guess when the next wave will crash upon the shore. The energy released during a solar flare can have profound effects on Earth. As these bursts of energy collide with our planet's magnetic field, they can induce geomagnetic storms, leading to disruptions in communication systems, navigation satellites, and even power grids. This interdependence between the Sun and Earth emphasizes the importance of ongoing research in solar physics. How can we better prepare for these solar storms? What measures can be taken to safeguard our technology in an increasingly interconnected world? The implications of solar flares extend far beyond our planet. They can influence the atmospheres of other celestial bodies, including planets and moons in our solar system. For instance, the Martian atmosphere has been significantly affected by solar activity, which has stripped away its protective layers over billions of years. Understanding this interaction provides insights into the evolution of planetary atmospheres, highlighting the sun's role in shaping the conditions for life. The pioneering work of scientists like Eugene Parker, who proposed the existence of the solar wind, has laid the groundwork for our current understanding of solar flares. Parker's groundbreaking ideas about the interaction between the solar wind and the Earth's magnetosphere have paved the way for a deeper exploration of the sun's impact on our planet. His work reminds us that curiosity and inquiry are fundamental to uncovering the mysteries of the cosmos. As we immerse ourselves in the study of solar flares, we also explore the broader implications for our understanding of astrophysics. These energetic events challenge us to consider the dynamics of other stars and the potential for habitable worlds beyond our own. Each solar flare is a reminder that the universe is alive, constantly evolving, and filled with wonder. Imagine standing beneath a starry sky, contemplating the vastness of the universe and the countless solar flares that dance across the cosmos. Each flare is not merely an explosion of energy, but a testament to the intricate processes at work within stars. The study of solar flares invites us to dream of distant worlds and the complex interplay of forces that shape them. The importance of solar flares in astronomy extends to their role in understanding stellar evolution. By studying the characteristics and behaviors of solar flares, scientists can gain insights into the life cycles of stars, their magnetic fields, and the potential for life in other solar systems. As we investigate these cosmic phenomena, we find ourselves drawn into a narrative that spans the universe, weaving together the stories of stars and the planets that orbit them. In this exploration, we also find ourselves faced with the enormity of our own existence. The sun, with its solar flares, serves as a powerful reminder of the forces that sustain life on Earth. The delicate balance of energy and matter that enables our world to thrive is a reflection of the intricate dance of cosmic elements at play. Each solar flare, while a momentary burst of brilliance, carries with it the weight of the universe's history and the promise of discovery. As we continue to study these phenomena, we embrace the unknown, allowing our curiosity to guide us toward new revelations and insights. The journey into the heart of solar flares is not merely an academic pursuit. It is a journey into the very essence of our cosmic existence, where each moment holds the potential for enlightenment and understanding. Through this exploration, we cultivate a deeper appreciation for the sun and its role in our lives, recognizing the profound connections that bind us to the cosmos. The energy of solar flares, while powerful and sometimes disruptive, also serves as a reminder of the beauty and complexity of the universe. As we learn more about these spectacular events, we also learn more about ourselves and our place within the grand tapestry of existence. Chapter 2. The Sun's Structure, where Flares Originate. The Sun is a magnificent sphere, an intricate assembly of layers, each with its distinct purpose and function. At the core lies the heart of this celestial body, where nuclear fusion takes place, creating an almost unimaginable energy output. This core is surrounded by the radiative zone, where energy produced in the core travels outward, bouncing around in a slow dance through dense plasma. Imagine particles colliding, sharing energy, and moving ever closer to the surface, a vibrant journey that can take millions of years. Above the radiative zone is the convective zone, a turbulent layer where hot plasma rises, cools, and sinks back down, forming convection currents. It is in this realm that the sun's energy is transported to its surface, culminating in the photosphere, which is the layer we observe as the sun itself. This is where the light we perceive radiates into space, bathing our planet in warmth and illuminating our days. But the sun is not merely a source of light. It is a dynamic entity filled with processes that give rise to spectacular phenomena. The solar atmosphere consists of several layers, including the photosphere, the chromosphere, and the corona. Each layer plays a crucial role in the sun's behavior, especially when it comes to solar flares. The photosphere, while vibrant, is often only the beginning of the story. Just above it lies the chromosphere, a thin layer that can be seen during a total solar eclipse as a reddish glow. This layer is where the temperature begins to rise, setting the stage for the energetic events that follow. Above the chromosphere is the corona, the sun's outer atmosphere extending millions of kilometers into space. The corona is a realm of extremes, with temperatures soaring to millions of degrees, far hotter than the layers beneath it. It is in this layer that the magnetic fields become particularly important, acting as a catalyst for solar flares. Solar flares originate from the sun's magnetic fields, which are generated by the motion of charged particles within the sun. These magnetic fields are not static, they are dynamic and can twist and tangle, creating potential energy. When the magnetic field lines break and reconnect, this stored energy is released in a rapid burst, resulting in a solar flare. This process is akin to a coiled spring, suddenly released after being held in tension. The energy unleashed can produce radiation across the entire electromagnetic spectrum, affecting everything from radio communications to the auroras we see on Earth. To grasp how this magnetic field activity leads to flares, one can consider the work of scientists like Richard Carrington, who, in the mid-19th century, made significant contributions to our understanding of solar phenomena. Carrington observed a solar flare and its effects on Earth's magnetic field, paving the way for future research. He once noted that the sun is a vast, complex system, and his insights helped to illuminate the connections between solar activity and terrestrial effects. Sunspots, those dark blemishes on the sun's surface, are intrinsically linked to solar flare activity. They are regions of intense magnetic activity, where magnetic field lines are concentrated. Sunspots can appear in groups, forming larger structures known as active regions. The presence of these spots indicates a higher likelihood of solar flares, as the magnetic fields in and around them become increasingly unstable. Imagine these sunspots as the quiet eye of a storm, where the surrounding turbulence is ready to erupt into a powerful release of energy. When sunspots are particularly abundant, we witness an increase in solar activity, leading to more frequent and intense flares. This correlation between sunspots and flares is a crucial aspect of solar physics. As solar physicist John F. D. McCarthy observed, sunspots are the fingerprints of the sun's magnetic activity. Through careful observation and study of these spots, scientists can predict potential flare events, offering insights into the sun's behavior and its impact on our planet. As we visualize the sun's layers, we can imagine the convective currents swirling in the convective zone, sending streams of energy upward while the magnetic fields twist and weave through the corona. Picture the sunspot regions, dark but full of energy, ready to spring to life with explosive force. The solar atmosphere acts as a conduit for these energetic events. When a flare occurs, the energy released causes a rapid rise in temperature and pressure in the surrounding plasma, which can lead to coronal mass ejections. These massive bursts of solar wind and magnetic fields can travel through space, impacting Earth's magnetosphere and igniting beautiful auroras at the poles. The connection between the sun's layers and its explosive events is a reminder of the intricate balance within our star. Each layer, from the core to the corona, is essential in creating the conditions necessary for solar flares to occur. As we deepen our understanding of these processes, we begin to see the sun not just as a source of light, but as a complex system that influences life on Earth in profound ways. Imagine standing outside on a clear night, gazing up at the stars, knowing that the light you see has traveled millions of kilometers to reach you. Now consider that some of this light could have originated from an explosive solar flare, a brief moment of brilliance that ripples through space. The interplay between the sun's structure and its magnetic fields creates a dynamic environment where flares can emerge, reminding us of the powerful forces at play in our universe. As we continue to explore the sun's behavior, we encounter the concept of solar cycles, periods during which the sun's activity waxes and wanes. These cycles typically last around 11 years, and during periods of maximum activity, the frequency of sunspots and solar flares increases. The rhythmic nature of these cycles illustrates the sun's complex behavior, revealing a dance of magnetic fields and plasma flows that shapes our solar system. Throughout history, the sun has been a subject of fascination, its cycles influencing cultures and civilizations. From ancient times to modern astronomy, the sun has been revered, studied, and marveled at. It is a reminder of our place in the cosmos, a constant source of energy and life that also harbors the potential for destructive power. Understanding the sun's structure and the mechanisms behind solar flares enriches our appreciation of this celestial giant. As we look to the sky, we can contemplate the intricate layers that define our sun and the magnetic fields that govern its explosive behavior, creating a tapestry of energy that connects us to the universe. The sun, in all its complexity, serves as a reminder of the wonders of science and the beauty of our natural world. Each flare, each sunspot speaks to the dynamic processes at work, urging us to continue exploring and seeking knowledge about the forces that shape our existence. With every observation, we gather threads of understanding, weaving a deeper narrative about the sun and its profound impact on life here on Earth. Amid the sun's dynamic layers, the interplay of magnetic fields and plasma creates a captivating spectacle that continues to intrigue scientists. The solar atmosphere, with its intricate dance of charged particles, is a critical player in the formation of solar flares. It is a vast expanse where the properties of plasma, an ionized state of matter abundant in the universe, come into play. Visualize this plasma as a vibrant sea of charged particles, swirling and shifting, each influenced by the magnetic forces at work. As we observe the chromosphere and corona, we see that these layers are not merely passive bystanders. They are active participants in the solar phenomena that shape our skies. The corona, in particular, is a realm of extreme conditions. Here, temperatures soar to millions of degrees, creating a stark contrast with the cooler layers below. This intense heat is primarily due to the energy released from the magnetic reconnection processes that give rise to solar flares. Imagine witnessing a solar flare erupting from the corona, a brilliant flash of light that can release energy equivalent to millions of megatons of TNT. This immense energy produces a surge of radiation across the electromagnetic spectrum, affecting not only the sun's immediate environment, but also extending its influence to Earth. The effects can be profound, leading to disturbances in communication systems and even triggering spectacular auroras in the polar regions. The magnetic fields responsible for these events are generated by the movement of charged particles within the sun. These fields can become twisted and tangled, accumulating energy until they reach a breaking point. When this occurs, the reconnection of magnetic field lines releases energy in a manner akin to a tightly coiled spring snapping back into its original shape. The sheer force of this release can propel particles into space at incredible speeds, creating solar winds that ripple through the solar system. As we contemplate this process, we are drawn to the observations made by figures like George Ellery Hale, a pioneer in solar physics. His work in the early 20th century revealed the connection between sunspots and magnetic activity, emphasizing that the sun is a complex and dynamic system of magnetic fields. Hale's insights laid the groundwork for our understanding of how solar flares are intricately linked to the sun's magnetic architecture. Sunspots themselves are fascinating indicators of solar activity, often appearing in cycles that mirror the sun's overall behavior. When we see sunspots clustering on the sun's surface, it signals heightened magnetic activity. These regions are cooler than their surroundings, shrouded in magnetic fields that inhibit the flow of heat, creating visible dark patches. Imagine gazing at the sun through a telescope, spotting these enigmatic spots scattered across its surface. Each sunspot is more than just a blemish. It is a window into the sun's inner workings. The magnetic fields associated with sunspots can become highly unstable, leading to the explosive release of energy during a flare. This dynamic interplay is crucial for understanding solar phenomena, as the presence of sunspots increases the likelihood of solar flares erupting in their vicinity. The relationship between sunspots and solar flares is not merely a coincidence. It is a reflection of the sun's broader magnetic behavior. During solar maximum, when sunspots are abundant, we experience a surge in solar flares. Conversely, during solar minimum, the sun appears more tranquil, with fewer sunspots and diminished flare activity. This cyclical nature offers a glimpse into the rhythms of our sun, reinforcing the notion that it is a living entity, consistently evolving and changing. As we consider the solar cycles, it is intriguing to reflect on how these patterns have shaped human history. Ancient civilizations often looked to the sun for guidance, its cycles informing agricultural practices and cultural rituals. Today, our scientific understanding of these cycles continues to evolve, offering insights into the sun's behavior that were once mere speculation. The connection between solar activity and its effects on Earth extends beyond the immediate impact of solar flares. For instance, the energetic particles released during a flare can interact with Earth's magnetic field, leading to geomagnetic storms. These storms can induce currents in power lines, potentially disrupting electrical systems and satellite communications. Such events underscore the importance of monitoring solar activity, allowing us to prepare for potential disruptions in our increasingly technology-dependent world. Furthermore, the beauty of the auroras, those ethereal displays of light dancing across polar skies, serves as a reminder of the sun's influence on our planet. These captivating phenomena are born from the interaction of solar wind particles with Earth's magnetic field, creating a breathtaking light show that has inspired countless generations. As we stand in awe of the cosmos, it is essential to appreciate the delicate balance of forces that govern our sun. Each solar flare is not merely a brief burst of brilliance. It is a testament to the complex processes at work within the sun's layers. The layers of the sun, from the core to the corona, are interconnected in ways that reveal a stunning portrait of energy in motion. In contemplating the sun's structure and the role of magnetic fields, we invite a sense of wonder about our place in this vast universe. Each observation of the sun serves as a reminder of the mysteries that lie beyond our atmosphere, urging us to explore further and seek knowledge about the forces that shape our existence. With every solar cycle, we gain insights into the sun's behavior, deepening our understanding of its impact on our planet and the broader cosmos. The sun, a constant companion in our lives, continues to illuminate the path of discovery, guiding us through the wonders of science and the beauty of nature. In this intricate dance of energy and light, we find not only the story of the sun, but also the story of ourselves, woven together in the fabric of the universe. Chapter 3. Mechanisms behind solar flares, the science. Solar flares, those breathtaking bursts of energy, have their roots deeply embedded in the complex interplay of magnetic forces within the sun. At the heart of these phenomena lies a process known as magnetic reconnection, a captivating mechanism that fuels the explosive release of energy we observe during a flare. Picture the sun as a vast, swirling mass of charged particles, where magnetic field lines twist and turn like intricate threads woven throughout its surface. Magnetic reconnection occurs when these magnetic field lines, which are constantly shifting due to the sun's turbulent atmosphere, break and then reconnect in a different configuration. This rearrangement releases an enormous amount of energy, transforming magnetic energy into kinetic energy and thermal energy. Imagine a tightly coiled spring suddenly released. What was once potential energy is now unleashed in a rapid explosion. In the context of solar flares, this transformation results in the release of energy equivalent to millions of hydrogen bombs detonating simultaneously, illuminating the sun's surface with brilliant flashes of light. As the magnetic fields reconnect, they can accelerate charged particles to incredible speeds. These particles, primarily electrons and protons, rush outward into space, creating shock waves that can lead to the formation of coronal mass ejections. The energy released during these events is not just confined to the immediate vicinity of the flare. It radiates outward across the electromagnetic spectrum. This is why we can observe solar flares in various wavelengths, from radio waves to X-rays, providing a rich tapestry of data for scientists to analyze. Within this dynamic interplay of energy, plasma plays a pivotal role in the flare's dynamics. Plasma, often referred to as the fourth state of matter, consists of charged particles that are influenced by electric and magnetic fields. The sun's plasma is highly ionized, creating an environment where electric currents can flow freely. During a solar flare, this plasma is heated to millions of degrees, causing it to emit vast amounts of radiation. The temperature and density changes in this plasma can lead to intricate structures forming, like loops and arcs, visible in high-resolution images taken by solar observatories. Imagine gazing at the sun's surface through a powerful telescope, witnessing these structures evolving in real time. The observations reveal how the plasma behaves under extreme conditions, creating a ballet of light and energy. The sun's corona, in particular, becomes a canvas for these dramatic events, displaying tendrils of plasma that stretch far into space, sometimes even reaching Earth. The observational techniques used to study solar flares have evolved significantly, providing researchers with unprecedented insights into these spectacular phenomena. High-tech instruments, such as space-based telescopes and ground-based observatories, capture images and data across multiple wavelengths. For instance, the Solar Dynamics Observatory continuously monitors the sun in various bands, offering a detailed view of solar activity. Imagine being able to see the sun's surface in ultraviolet light, revealing the hidden dynamics of the solar atmosphere. These observations help scientists understand the temperature fluctuations and the behavior of magnetic fields during flare events. Additionally, radio telescopes detect the radio emissions produced by the accelerated particles, unraveling further layers of complexity. The development of advanced imaging techniques, such as imaging spectroscopy, has allowed researchers to analyze the light emitted by solar flares in exquisite detail. This enables them to discern the velocities and temperatures of the plasma involved in the flares, enhancing our understanding of the energy release mechanisms. Throughout history, outstanding individuals have dedicated their lives to unraveling the mysteries of solar flares. One such figure is George Ellery Hale, who played a critical role in advancing our understanding of solar magnetism. Hale's contributions laid the groundwork for the field of solar physics, allowing future generations to probe deeper into the sun's magnetic activity. His passion and curiosity about the sun echo in the words he shared. The sun is a vast and complicated machine, and it is not easy to understand. As we explore the mechanisms behind solar flares, we are reminded of the luminous force that is the sun, constantly shaping our world. The intricate processes of magnetic reconnection and plasma dynamics not only illuminate the sun's surface, but also serve as a testament to the vastness of our universe. The energy released during these events reaches far beyond the sun itself, influencing space weather and affecting life on Earth in profound ways. In this ongoing quest to understand solar flares, we continue to refine our observational techniques and deepen our knowledge. The journey of discovery is as dynamic as the sun itself, inviting us to ponder the mysteries of our nearest star. What else lies beneath the surface? What new revelations await us as technology advances and our understanding evolves? As we contemplate these questions, we appreciate the beauty of the sun's energy and the interplay of forces that create such magnificent phenomena. Each solar flare tells a story, a reminder of the cosmic dance that shapes not only our solar system, but also our very existence. The sun's powerful embrace continues to inspire awe and curiosity, urging us to look up and wonder at the celestial symphony unfolding above. As we delve further into the intricate world of solar flares, the process of magnetic reconnection reveals itself as a mesmerizing cascade of energy transformation. This event is not merely a singular occurrence. It represents a symphony of interactions among charged particles, magnetic fields, and plasma dynamics that together create the stunning phenomena we observe. The energy released during a solar flare is staggering. When magnetic reconnection occurs, it is akin to releasing the tension in a tightly wound coil. This sudden liberation generates an expansive burst of energy that can be detected across the electromagnetic spectrum. Imagine the sun pulsating with intensity, sending out waves of radiation that travel across vast distances. Photons emitted during these events can reach Earth in mere minutes, while the effects of the particles released can take longer, sometimes days, to arrive. This energy is not simply a flash in the cosmic pan, it is a potent force with real implications for our planet. The intense bursts of electromagnetic radiation can interfere with our technology, disrupting radio communications and impacting satellite operations. Scientists have observed how these solar flares can create disturbances in the Earth's magnetosphere, leading to beautiful yet potentially disruptive auroras, as charged particles collide with atmospheric gases. The delicate balance between the sun's energy and life on Earth underscores the interconnectedness of our existence, inviting us to ponder the delicate threads that bind us to our nearest star. The role of plasma in the dynamics of solar flares cannot be overstated. Plasma, a state of matter that comprises the majority of the universe, behaves in ways that are both fascinating and complex. In the sun's atmosphere, this plasma is not just a passive medium, it is an active player in the dance of energy release. As solar flares erupt, the plasma becomes superheated to millions of degrees, transforming into a brilliant spectacle. Imagine witnessing this process unfold, where the sun's atmosphere glows with an ethereal light, revealing structures that twist and spiral as they are influenced by the ever-changing magnetic fields. In these moments, one might ask, what drives the behavior of this superheated plasma? The answer lies in the interplay of magnetic forces and the inherent properties of plasma itself. Charged particles within the plasma respond to magnetic fields, creating currents that can amplify the energy present. This self-reinforcing cycle enhances the conditions for a flare, as the energy builds and awaits the moment of release. The complexity of these interactions speaks to the beauty of our universe. where even the simplest elements engage in a dynamic interplay that can lead to extraordinary outcomes. Observational techniques have advanced significantly, allowing scientists to uncover the mysteries of solar flares with remarkable precision. High-resolution imaging from space-based observatories such as the Solar and Heliospheric Observatory has provided unprecedented views of these phenomena. Researchers utilize a variety of wavelengths to gather a comprehensive understanding of solar activity. Each wavelength offers a unique perspective. For instance, ultraviolet and X-ray observations reveal the hottest regions, while radio emissions allow us to trace the paths of accelerated particles. Consider the role of spectroscopy in this endeavor. By analyzing the light emitted from solar flares, scientists can glean insights into the physical conditions within these explosive events. The spectral lines produced by the plasma reveal crucial information about temperature, density, and even the velocities of the particles involved. Imagine the thrill of piecing together the puzzle of a solar flare through the prism of light, each observation adding depth to our understanding. Throughout history, numerous pioneering scientists have contributed to our growing knowledge about solar phenomena. One notable figure is Richard Carrington, who, in the mid-19th century, made significant strides in understanding solar flares. He was the first to observe a solar flare and correlate it with geomagnetic storms on Earth. His groundbreaking work laid the foundation for future studies and highlighted the profound connection between solar activity and terrestrial effects. Carrington's passion for exploration and discovery resonates in his assertion that the sun is a magnificent star, the source of all life and energy on Earth. As we continue to explore the mechanisms behind solar flares, the pursuit of knowledge is as dynamic as the sun itself. Each discovery opens new avenues of inquiry, inviting further investigation into the intricate processes at play. What secrets remain hidden within the sun's layers? How will advancements in technology and observational capabilities enhance our understanding of these radiant bursts of energy? The sun, in its enigmatic glory, remains an endless source of wonder and inspiration. As we ponder the complexities of solar flares, we are reminded of the delicate balance that governs our universe. Each flare serves as a testament to the powerful forces at work, shaping not only the sun but also the very fabric of our existence. In this cosmic dance, we are participants, forever intertwined with the rhythms of the solar system and the mysteries that unfold above us. Within the radiant chaos of a solar flare, the role of plasma is not merely passive, it is central to the unfolding drama. Plasma, often described as an ionized gas, is abundant in the sun's atmosphere and behaves in unique ways under the influence of magnetic fields. Imagine a vast cloud of charged particles swirling in a brilliant dance, each particle influenced by the magnetic forces that govern their interactions. This interaction is crucial during a flare, as the temperature skyrockets, elevating the plasma to millions of degrees. The result is a luminous spectacle, with streams of superheated gas illuminating the sun's corona. As the plasma becomes energized, it creates a dynamic environment where electric currents flow freely. These currents further intensify the magnetic fields, leading to a feedback loop that can escalate the conditions for a flare. Picture this scenario. A gentle breeze transforms into a powerful storm, fueled by the very elements that once seemed calm. In the sun's atmosphere, this transformation can be sudden and overwhelming, giving rise to explosive releases of energy. The energy output during a solar flare can be astonishingly high. In a matter of minutes, a single flare can release more energy than humanity consumes in an entire year. This intensity is not just a fleeting moment. It reverberates throughout the solar system. The charged particles released during these flares travel at incredible speeds, creating waves of energy that can interact with the Earth's magnetic field. Such interactions can lead to geomagnetic storms, which can disrupt satellite operations and even affect electrical grids. The observational techniques used to study these phenomena have rapidly advanced, allowing scientists to gather intricate details about solar flares. Space-based observatories continually monitor the sun, capturing data across a spectrum of wavelengths. For instance, the bright flashes in X-ray and ultraviolet light provide insight into the plasma dynamics within a flare. Imagine being able to witness these bursts of energy unfold in various colors, each hue revealing a different aspect of the solar event. Spectroscopic observations play a pivotal role in this research, allowing scientists to analyze the light emitted by solar flares in great detail. By examining the spectral lines, researchers can determine the temperature and density of the plasma involved in these explosive events. What stories do these lines tell about the conditions within a flare? They reveal the velocities of particles, the magnetic field strengths, and the overall energy distribution, helping us piece together the intricate puzzle of solar activity. Many distinguished scientists have contributed to our understanding of solar flares, each adding their unique perspective to the unfolding narrative. Consider the contributions of the astrophysicist and solar physicist Maria Weber, who has dedicated her career to understanding the intricate behaviors of the solar atmosphere. Her insights into the mechanisms of energy release during solar flares have opened new pathways for research, demonstrating that the sun is not just a distant star, but a complex, dynamic system that influences our world. As the sun continues to evolve, so too does our understanding of its powerful phenomena. The mechanisms behind solar flares are a reminder of the delicate balance within the sun's atmosphere, where energy and plasma interact in marvelous ways. Each flare is a testament to the sun's vitality, inviting us to explore further and uncover the mysteries hidden beneath its radiant surface. What new technologies will emerge to enhance our observations? How will future discoveries reshape our understanding of solar physics? In contemplating these questions, we find ourselves woven into the grand narrative of the cosmos. The sun, in all its brilliance, is a beacon of energy and a source of wonder. Each solar flare, with its vibrant display and profound implications, serves as a reminder of our connection to the universe, urging us to gaze upward and marvel at the celestial wonders above. Chapter 4. Types of solar flares, Classification and Characteristics. Solar flares, those breathtaking bursts of energy, can be classified into distinct categories based on their intensity and impact. Understanding these classifications helps illuminate the varied nature of solar activity and its effects on our planet. While all flares originate from the sun's magnetic fields and the intricate dynamics within its layers, they differ significantly in their intensity and the potential consequences for Earth. The primary types of solar flares are categorized into three main classes: X-class, M-class, and C-class flares. Each classification represents a different level of intensity, much like a scale that measures the energy of these cosmic events. X-class flares are the most powerful among them, releasing an extraordinary amount of energy. Imagine the sheer force of 1,000,000 hydrogen bombs igniting simultaneously. Such intensity can have profound effects on our technological systems, disrupting radio communications and even affecting power grids. Next in line are the M-class flares. While they are less intense than X-class flares, they still pack a significant punch, releasing enough energy to cause some disruption, but on a smaller scale. These flares can lead to moderate radio blackouts and increase radiation exposure for astronauts in space. Then there are the C-class flares, the mildest of the three. Although they emit less energy, they still serve as a reminder of the sun's dynamic nature. C-class flares rarely have noticeable effects on Earth, but they are nonetheless a part of the sun's ever-changing behavior. It is fascinating to consider how the classification of solar flares reflects their potential impact on solar activity as a whole. The intensity of a flare can indicate the level of magnetic activity on the sun. High-intensity flares, like the X-class, often coincide with periods of heightened solar activity, such as solar storms or coronal mass ejections. These events can unleash a torrent of charged particles into space, which can interact with Earth's magnetic field, leading to stunning auroras, or, in more severe cases, geomagnetic storms that can disrupt satellite operations and communication systems. Historically, some notable solar flares have captured the attention of scientists and the public alike. One such occurrence was the solar flare in the year of the early 1980s, which unleashed a powerful burst of energy that caused radio blackouts across the Pacific Ocean. The intensity of the event left many wondering about the sun's mysterious behavior and its influence on our daily lives. Scientists, including renowned solar physicists, have dedicated their careers to unraveling the complexities behind such phenomena, with the aim of predicting their occurrences and understanding their implications for life on Earth. Another significant event was the solar flare that took place in the mid-2000s, during a period of heightened solar activity. This flare was remarkable not only for its intensity, but also for the technological advancements that allowed scientists to observe and analyze it in real time. The ability to track and study these events has expanded our understanding of solar physics, leading to enhanced models of solar behavior and improved forecasting techniques. As one prominent astrophysicist aptly stated, "The sun is a powerful force, and understanding its behavior helps us navigate our own existence." Imagine the thrill of witnessing a solar flare erupt in vivid hues of orange and yellow, radiating energy across the cosmos. Such moments remind us of the sun's dynamic character and its role in the universe. Each flare, regardless of its class, tells a unique story, reflecting the ongoing processes within the sun and the vastness of the solar system. As we explore the classifications of solar flares, it is essential to appreciate the intricate interplay of forces at work. The sun's surface, with its turbulent plasma and magnetic fields, is a stage where these phenomena unfold. Each flare, categorized by its intensity, serves as a testament to the sun's energy and the forces that shape our solar system. The echoes of these flares can be felt on Earth, reminding us of our connection to this celestial body. When an X-class flare erupts, it sends shockwaves through the solar system, and we, on our little planet, become part of this grand cosmic narrative. The energy released can create beautiful auroras in the polar regions, painting the night sky with shimmering lights, a stunning reminder that the sun's activity has both a fierce and a delicate side. This classification system not only aids scientists in their research, but also bridges the gap between the sun's explosive activity and our day-to-day lives. By understanding the types of solar flares, we can better prepare for their impacts, whether it be shielding technology from potential disruptions or simply marveling at the beauty of nature's light show. As we gaze upon the sun, whether from our backyards or through powerful telescopes, we witness a cosmic dance of energy and matter. Each type of flare, each classification, reveals a layer of complexity that speaks to the magnificence of our universe. The sun continues to be a source of inspiration and inquiry, urging us to delve deeper into its mysteries, to explore and understand the forces that not only illuminate our days, but also shape the very fabric of our existence. In this ever-evolving study of solar flares, we find an invitation to engage with the cosmos. As we learn about the distinctions between X-class, M-class, and C-class flares, we also embrace the wonder of scientific discovery. Each classification is a reminder that the universe is alive, teeming with energy and stories waiting to be uncovered. So as we reflect on the sun's fiery personality and its flares, let's remember the interconnectedness of these cosmic events with our lives. The energy that radiates from the sun does not merely illuminate the sky. It is a vital force that influences technology, weather, and even the rhythms of life on Earth. Understanding the classifications of solar flares empowers us to appreciate the beauty and complexity of our solar system, inviting us to remain curious and engaged with the world around us. The classification of solar flares not only highlights their intensity, but also sheds light on the underlying dynamics of solar activity. The sun, with its complex structure and turbulent atmosphere, is a constant source of energy and change. Each flare serves as a momentary glimpse into the sun's life cycle, revealing how magnetic forces and plasma interactions fuel its brilliance. Consider how X-class flares, the most potent of the three categories, often correlate with the sun's solar cycle. This cycle, lasting approximately 11 years, sees periods of heightened activity known as solar maximum, when sunspots proliferate and flares become more frequent. During these times, the sun can unleash multiple X-class flares within a single day. The relationship between solar cycles and flare activity invites a deeper understanding. How do these massive eruptions influence not only our technology, but also the natural phenomena we experience on Earth? M-class flares, while less intense, are not to be underestimated. They can still impact radio communications and navigation systems, particularly in polar regions where the Earth's magnetic field is weaker. The interplay between these flares and Earth's atmosphere can create fluctuations in radio signals, leaving scientists and operators in the field to ponder the balance between celestial mechanics and earthly operations. Imagine working on a crucial communication project, only to be interrupted by the sun's whims, reminding us of its power over our technological advancements. Even the mild C-class flares, which might seem inconsequential, contribute to a larger narrative of solar activity. They demonstrate that even the smallest bursts of energy can be part of a grander cycle of solar phenomena. These flares often occur in clusters, suggesting that the sun's magnetic fields are always in motion, constantly reshaping and evolving. How might these subtle cosmic events influence our understanding of solar dynamics? Throughout history, humanity has attempted to connect solar flare occurrences with earthly consequences, often leading to a sense of awe and wonder. The solar flare in the early 1980s, for example, not only disrupted communications, but also sparked curiosity about the sun's behavior. It was a call to action for scientists to develop better predictive models and systems to understand these cosmic events. What lessons can we learn from these past occurrences, and how can we apply that knowledge to future solar activity? The remarkable solar flare event of the mid-2000s stands as a testament to our evolving relationship with the sun. During this time, advancements in observational technology allowed scientists to capture real-time data, revealing the intricacies of flare dynamics. The ability to monitor solar flares with unprecedented precision has transformed our understanding, enabling researchers to analyze the characteristics of various flares and their potential impact on Earth's environment. This leap in scientific capability prompts us to consider, how does real-time data change our approach to solar phenomena? Among the many scientists who have contributed to our understanding of solar flares, one stands out for her groundbreaking research. Renowned astrophysicist Dr. Margaret Kivelson has explored the interactions between solar activity and planetary atmospheres. Her work emphasizes the importance of understanding the sun's influence on magnetospheres and atmospheres, revealing the profound connections between solar flares and the conditions necessary for life on other planets. As she famously stated, "We are all made of stardust, and understanding the sun is key to understanding our own existence in the cosmos." As we ponder the implications of solar flares, we also reflect on their beauty. Imagine standing under the night sky, witnessing the aftermath of a powerful solar flare as it ignites the auroras dancing across the polar regions. These vibrant displays are a direct result of the sun's energetic outbursts interacting with Earth's magnetic field. The colors swirling in the atmosphere remind us that the sun's energy resonates far beyond its own surface, connecting us to the universe in profound ways. The role of solar flares extends into the realm of climate science as well. The energetic particles released during intense solar events can influence the upper atmosphere, potentially affecting weather patterns on Earth. While the direct correlation between individual flares and weather is still under investigation, the interconnectedness of solar activity and terrestrial phenomena is undeniable. What wonders might we uncover by further exploring this relationship? As we continue to observe the sun and its flares, we are reminded of the delicate balance of forces at play. The sun's magnetic fields, its plasma dynamics, and the energetic dance of charged particles all converge to create these magnificent eruptions. Each flare, regardless of its classification, contributes to a greater understanding of solar physics and its implications for our world. In the intricate web of solar activity, we find an invitation to engage with the cosmos, to reflect on our place within this vast universe. The sun, a celestial beacon, sparks curiosity, inspires exploration, and reminds us of the power and beauty of nature. Each solar flare tells a story, a narrative woven into the fabric of time and space, urging us to forge a deeper connection with the cosmos. As we observe the sun and its vibrant displays, we are drawn into a realm of wonder and inquiry. The classification of solar flares serves not just as a scientific tool, but as a bridge connecting us to the forces that shape our existence. Each flare, whether X-class, M-class, or C-class, embodies the sun's energy and its profound impact on every aspect of life on Earth and beyond. Chapter 5. Impacts on Space Weather. What happens next? As we reflect on the magnificent phenomena of solar flares, it becomes essential to explore their profound relationship with space weather. Solar flares are not isolated events. They are dynamic forces that ripple through the vastness of space, influencing the environment around our planet. Imagine these flares as powerful echoes, sending shockwaves across the solar system, weaving an intricate narrative of interaction between the sun and the Earth. When a solar flare erupts, it releases an immense amount of energy, leading to a surge of electromagnetic radiation. This radiation travels at the speed of light, reaching Earth in mere moments. But the impact of a solar flare extends far beyond just light and radiation. One of the most significant effects of a solar flare is its influence on the Earth's magnetosphere, the protective magnetic field that envelops our planet. Picture the magnetosphere as a shield, a bubble that guards us from the solar wind and cosmic radiation. As solar flares release their energy, they can compress this magnetic field, distorting its normal shape. This interaction can create a cascade of effects, influencing not only the magnetosphere, but also the upper atmosphere. As the charged particles from the solar flare encounter the Earth's magnetic field, they can trigger geomagnetic storms. These storms, resulting from the interplay of solar wind and the Earth's magnetosphere, can cause a dazzling display of auroras, transforming the night sky into a vibrant canvas painted with greens, reds, and purples. Imagine standing under such a sky, feeling the connection between the Earth and the cosmos as the colors dance overhead. It is a reminder of how intertwined our existence is with the sun's activity. The geomagnetic storms that follow solar flares can have both beautiful and disruptive consequences. While they create stunning visual spectacles, they can also disturb satellite operations, disrupt navigation systems, and even affect power grids. The solar wind plays a critical role in this complex interaction. It is a continuous stream of charged particles emitted by the sun, flowing through space at high speeds. When a solar flare occurs, it can enhance the solar wind, sending a wave of particles racing towards Earth. This enhanced solar wind interacts with the magnetosphere, leading to an increased likelihood of geomagnetic storms. Picture the solar wind as a river flowing through the vast expanse of space, occasionally swelling with the force of a solar flare, altering the landscape of the Earth's magnetic field. Prominent figures in the field of space weather have emphasized the importance of understanding these phenomena. One such luminary, Dr. Frank Pavone, has noted, "Solar flares can change the space weather dramatically, affecting everything from satellites to power grids on Earth." This quote encapsulates the urgency with which scientists approach the study of solar activity and its implications for our daily lives. As we consider the impacts of solar flares on space weather, we must also acknowledge the historical context of these interactions. Throughout history, significant solar events have been recorded, often coinciding with disruptions on Earth. For instance, The Carrington event of 1869 stands as a poignant reminder of the power of solar flares. This colossal solar storm, which followed a series of intense flares, caused widespread telegraph outages and auroras visible as far south as the Caribbean. The interplay between solar activity and technological systems is a narrative that continues to unfold today. The occurrence of geomagnetic storms following solar flares is a testament to the intricate balance of forces within our solar system. As the charged particles collide with the Earth's magnetic field, they can create currents that flow through the atmosphere and into the ground. This process can induce electric currents in power lines, leading to voltage fluctuations and even transformer failures. Imagine the delicate dance of energy as it moves from the heavens, through the atmosphere, and into our technological systems, reminding us of our vulnerability to the forces of nature. The solar wind, with its relentless flow of particles, can enhance these geomagnetic storms. When the solar wind reaches Earth, its speed and density can vary based on the sun's activity. During periods of heightened solar activity, such as during a solar flare, the solar wind can become particularly intense, amplifying the effects on the magnetosphere. This serves as a reminder of the sun's dynamic nature and its ability to influence the environment of our planet. As we delve deeper into the relationship between solar flares and space weather, we begin to appreciate the complexity of this cosmic dance. The sun's activity is not merely a spectacle. It is a crucial element that can shape our technological landscape. Scientists continually strive to better understand these interactions, not only to predict solar events, but also to mitigate their impacts on our lives. The significance of solar flares extends into our modern world, where technology is intricately woven into the fabric of daily life. The potential disruptions caused by geomagnetic storms can lead to significant challenges. For example, satellites orbiting the Earth may experience communication interruptions or damage to their systems due to the charged particles from solar flares. The implications for astronauts in space are equally profound. Space missions rely on precise navigation and communication, both of which can be compromised during intense solar activity. As Dr. Sunita Williams aptly put it, we need to be aware of space weather in order to protect our astronauts and our technology. Her insights highlight the importance of preparedness in the face of nature's powerful forces. As we contemplate the future, the study of solar flares and their impacts on space weather will only become more critical. With advancements in technology, scientists are now able to monitor solar activity in real time, allowing for more accurate predictions of solar flares and their potential consequences. Imagine a world where we can anticipate the effects of solar flares on Earth, enabling us to take proactive measures to safeguard our technology and infrastructure. The relationship between solar flares and space weather serves as a reminder of the interconnectedness of our universe. It invites us to consider how the sun, a seemingly distant celestial body, plays an integral role in our daily lives. With each solar flare, we are reminded of the sun's power and the delicate balance that sustains life on Earth. As we embrace this cosmic connection, it becomes evident that understanding solar flares and their impacts on space weather is not merely a scientific pursuit. It is an exploration of our place in the universe. The knowledge we gain from studying these phenomena can empower us to navigate the challenges posed by solar activity, fostering a deeper appreciation for the forces that shape our world. In the vast expanse of the cosmos, solar flares are but a fleeting moment, yet their impacts resonate far beyond their origin. They remind us of the beauty and unpredictability of the universe, urging us to remain vigilant and curious. As we continue our journey through this captivating field of study, we will uncover more of the sun's secrets, illuminating the path forward in our quest to understand the dynamics of space weather and its effects on our lives. The relationship between solar flares and space weather goes beyond mere observation. It involves understanding the mechanisms that drive these celestial events. As solar flares erupt, they unleash not only light, but also a torrent of charged particles into the solar wind, which can significantly alter the dynamics of space weather. These charged particles, primarily electrons and protons, can travel at astonishing speeds, creating a fascinating interplay between the Sun and the Earth. Imagine the solar wind as a vast ocean of particles, continuously flowing from the Sun. When a solar flare occurs, it acts like a powerful storm, sending ripples through this ocean. These ripples can influence the density and speed of the solar wind, leading to a greater likelihood of geomagnetic storms as they approach Earth. The intensity of the solar wind can vary, creating a dynamic environment that can either shield us or expose us to various space weather phenomena. As the solar wind interacts with the Earth's magnetosphere, it can compress and reshape this protective barrier. This compression can amplify the effects of the solar flares, leading to more pronounced geomagnetic activity. Picture how a gentle breeze caresses a surface, but when it turns into a gust, it can stir up more than just dust. It can reshape the landscape. Similarly, the enhanced solar wind during solar flares can lead to a significant increase in geomagnetic storms, transforming our magnetic shield into a dynamic realm of interaction. Geomagnetic storms are categorized based on their intensity and the potential impact they can have on technological systems. These storms can result in beautiful auroral displays as charged particles collide with atmospheric gases, creating a light show that captivates all who are fortunate enough to witness it. Yet, alongside this beauty lies the potential for disruption. During severe geomagnetic storms, satellites may encounter increased drag, affecting their orbits, while power grids can experience fluctuations that may lead to outages. Consider the impact of the solar wind on the Earth's magnetosphere as a conversation between two powerful entities. The Sun sends its energetic particles toward Earth, and in response, our planet's magnetic field reacts. This exchange is a dance of sorts, one that has been occurring for eons, shaping not only the space environment, but also the very fabric of life on Earth. Notable scientists have dedicated their careers to unraveling the intricacies of this relationship. Dr. David Hathaway, a prominent solar physicist, has emphasized the importance of understanding the Sun's behavior, stating, "Solar flares are the engines of space weather." His words resonate deeply within the scientific community, underscoring our need to decode the Sun's messages as they ripple through space and time. As we further explore the impacts of solar flares on the Earth's magnetosphere, we must consider the implications for human activities. The delicate balance we maintain with technology hangs in the balance, influenced by the whims of solar activity. For example, global positioning systems, which rely on satellites for accurate navigation, can experience errors during geomagnetic storms, leading to potential miscalculations. Imagine relying on a compass that can suddenly become erratic, steering you off course amid the vastness of an uncharted sea. The role of solar wind in these phenomena cannot be understated. During solar flare events, the solar wind can surge, heightening the interaction between the Earth and the Sun. This enhanced solar wind can lead to rapid changes in the magnetosphere, triggering a cascade of geomagnetic storms that can ripple through our technological networks. One of the most profound effects of geomagnetic storms is their ability to induce currents in power lines. These geomagnetically induced currents can flow through the Earth's surface, affecting electrical systems and leading to voltage irregularities. Imagine the unseen currents flowing through the ground, silently influencing the lights that illuminate our homes and the devices that connect us. As we look to the future, understanding the relationship between solar flares, solar wind, and geomagnetic storms becomes crucial. Advancements in technology and our growing knowledge of space weather allow us to monitor solar activity more effectively. Scientists now employ sophisticated satellite systems to observe solar flares and their subsequent effects on space weather. This real-time data equips us to prepare for potential disruptions, enabling us to anticipate challenges and protect our technological infrastructure. The Sun, a magnificent celestial body, continues to influence life on Earth in profound ways. Each solar flare serves as a reminder of our connection to the cosmos, urging us to remain vigilant and curious about the forces that shape our world. As we deepen our understanding of these phenomena, we nurture a sense of awe and respect for the dynamic interactions unfolding in the vastness of space. In contemplating the future, consider how the ongoing study of solar flares will illuminate our understanding of space weather and its impacts on our lives. With each discovery, we draw closer to demystifying the sun's behavior, fostering a greater appreciation for the intricate web of connections that bind us to the universe. The cosmos is a vast, ever-changing landscape, and as we journey through the realms of space weather, we find ourselves woven into the fabric of this extraordinary narrative, one that continues to unfold with every solar flare. Chapter 6. Effects on Communication Systems, Signal Disruptions. As we explore the intricate relationship between solar flares and communication systems, we begin to appreciate the profound impact these cosmic phenomena have on our everyday lives. Solar flares, with their explosive energy, can disrupt radio communications in ways that are both immediate and far-reaching. When a flare erupts, it releases a torrent of electromagnetic radiation that travels through space, reaching Earth almost instantaneously. This surge of energy can interfere with radio signals, particularly those that rely on high-frequency bands. Imagine a sudden storm rolling in, obscuring the clarity of your favorite song. A similar phenomenon occurs when solar flares unleash their energy into the atmosphere, creating a cacophony of static and distortion. During such disruptions, radio communications can experience blackouts or severe degradation. Pilots, maritime operators, and emergency services who depend on reliable radio signals may find themselves navigating through a cloud of uncertainty. The chaos that ensues can be likened to trying to listen to a whisper while standing amidst a bustling crowd. It is during these moments that the resilience of our communication systems is tested. The effects of solar flares extend beyond radio waves to influence the accuracy and reliability of global positioning system technology. GPS relies on signals transmitted from satellites orbiting Earth, and these signals can be easily affected by solar activity. When a solar flare occurs, the ionosphere, an atmospheric layer filled with charged particles, can become disturbed. This disturbance can lead to delays in signal transmission, causing inaccuracies in positioning. Imagine trying to follow a map on a foggy day. The lines of direction may blur, leaving you disoriented and unsure of your path. For those relying on GPS for navigation, whether on a leisurely drive or during crucial military operations, the implications can be significant. One can ponder the words of Dr. James Van Allen, a pioneer in the study of cosmic rays, who once said, quote, "The universe is full of surprises." The unpredictability of solar flares exemplifies this idea. Even with advanced technology and monitoring systems, predicting the exact moment and intensity of a solar flare remains a challenge. As we rely more heavily on GPS technology in our daily lives, understanding the impact of solar flares on the accuracy of these systems becomes increasingly important. The influence of solar activity on satellite operations cannot be overstated. Satellites are the silent sentinels of our modern world, providing vital data, communication, and navigation services. When solar flares occur, they can create a hostile environment for these technological marvels. The charged particles emitted during a flare can collide with satellite components, leading to potential malfunctions or even catastrophic failures. Picture a delicate flower caught in a sudden gust of wind, struggling to maintain its form against the onslaught of nature. Similarly, satellites must weather the fierce energy released during solar events. To illustrate this, consider the story of the Galaxy 15 satellite, which experienced a significant anomaly due to a solar flare. This satellite, which provides critical communication services, was rendered uncontrollable as it drifted off its intended path. Engineers and operators scrambled to regain control, working against time and the natural forces unleashed by the sun. Such instances reveal the vulnerability of our technological infrastructure to solar activity. and highlight the importance of monitoring space weather. Historically, communication failures linked to solar flares have been documented, showcasing the delicate balance between our technological advancements and the natural forces of the universe. One notable event occurred in 1989, when a powerful solar flare caused a massive geomagnetic storm. This storm disrupted power grids and communication systems, leading to widespread blackouts across parts of North America. The effects were felt not just in the immediate aftermath, but also in the days that followed, as operators worked diligently to restore services and assess the damage. Reflecting on this event, one may wonder how we can better prepare for such solar events in the future. The answer lies in a combination of scientific understanding and technological innovation. By studying past solar flares and their impacts, scientists can enhance predictive models to foresee potential disruptions. Continuous monitoring of solar activity allows for real-time assessments, providing valuable information to mitigate the effects of solar flares on communication systems. The advancements in space weather forecasting have also led to the development of protective measures for satellites. Engineers are now designing systems that can withstand the tumultuous conditions created by solar activity. Innovations such as adaptive shielding and radiation-hardened components are being implemented to ensure satellites remain operational even in the face of intense solar events. As we continue to delve into the ways solar flares disrupt communication systems, it becomes apparent that these cosmic phenomena are not merely challenges to overcome, but also opportunities for growth and resilience. Each flare serves as a reminder of the interconnectedness of our technological advancements with the natural world. In the vast expanse of the universe, the sun reigns supreme, its energy a double-edged sword that can illuminate our lives or cast shadows of uncertainty. As we gaze toward the stars, we find ourselves at the mercy of the sun's whims, yet we also stand on the precipice of discovery. The resilience of human ingenuity shines brightly as we strive to adapt and evolve in the face of these cosmic challenges. As we reflect on the impacts of solar flares, we may feel a sense of awe at the forces of nature. The sun, with its brilliant flares, continues to teach us about the delicate balance of our existence and the importance of respecting the powerful energies that shape our world. Each solar event is a reminder of our place in the cosmos, urging us to explore, learn, and innovate as we navigate the complexities of modern communication systems. The journey through the effects of solar flares on communication systems reveals a fascinating intersection of science, technology, and human experience. It invites us to imagine a future where we harness this knowledge to enhance our resilience against the forces of nature. As we continue to observe and learn from the sun's dynamic behavior, we embrace the challenge of preparing for whatever lies ahead, ensuring that communication remains a steadfast bridge connecting us to one another, even in the face of the sun's unpredictable energy. The repercussions of solar flares extend beyond immediate disruptions in radio communications and GPS technology. As we turn our attention to satellite operations, the complexity of these effects becomes even more apparent. Satellites serve myriad functions, from weather forecasting to global communications, and their seamless operation is crucial for modern society. Yet, the energy unleashed during a solar flare poses significant risks to these orbital guardians. Imagine a delicate instrument floating in the vastness of space, its sensors finely tuned to detect and transmit vital information. When a solar flare erupts, the surge of charged particles can inundate these instruments, disrupting their functionality. The delicate electronics within satellites can suffer from radiation damage, a phenomenon akin to a sudden surge of electricity overwhelming a finely crafted circuit. This can lead to temporary malfunctions, such as loss of signal or diminished operational capacity, or, in more severe instances, permanent failure of essential systems. One of the more striking instances of solar flares affecting satellite operations occurred with the Anik E2 satellite in the early part of the 21st century. This satellite, vital for telecommunications in Canada, experienced significant disruptions due to a geomagnetic storm triggered by solar activity. As the satellite systems faltered, engineers scrambled to devise solutions, illustrating the urgent need for resilience in the face of nature's unpredictability. The implications of such disturbances ripple through the fabric of daily life. When communication satellites falter, the effects can be felt in various sectors, from emergency services relying on clear signals to businesses dependent on uninterrupted connectivity. The question arises, how can we protect these critical technologies from the whims of solar phenomena? One avenue of exploration lies in the development of advanced shielding techniques to safeguard satellite components from radiation. Engineers are now focusing on materials that can absorb and deflect charged particles, providing an added layer of protection for essential satellite systems. Turning our gaze back to history, we unearth fascinating examples of communication failures attributed to solar flares. One notable incident unfolded in the late 20th century when a powerful solar storm caused widespread disruption to radio communications across Europe. The storm was so intense that it rendered many communication channels unusable, underscoring the fragile nature of our technological infrastructure. Operators were left scrambling to restore services while grappling with the realization that they were at the mercy of solar activity. Consider the words of a renowned astrophysicist who once remarked that the universe is the ultimate playground of the mind. This quote rings true as we explore the ways solar flares challenge our understanding of space and technology. The delicate dance between human innovation and celestial phenomena reminds us of our position within a grand cosmic ecosystem. Furthermore, the historical lens reveals how significant events have prompted advancements in our understanding of solar activity. For instance, the 1989 geomagnetic storm, which wreaked havoc in Quebec, served as a wake-up call for many. It galvanized efforts to improve forecasting models and implement protective measures for electrical grids and communication systems. The lessons learned from each incident contribute to a growing body of knowledge aimed at mitigating the impacts of solar flares. As we delve deeper into the relationship between solar flares and communication systems, the need for preparedness becomes increasingly evident. Real-time monitoring of solar activity, utilizing networks of satellites and ground-based observatories, has become a crucial element in safeguarding our technological infrastructure. But what does the future hold? Will we be able to predict solar flares with greater accuracy? Imagine a world where the dynamics of the sun are mapped with precision, where scientists can anticipate a solar flare's path and intensity. Such advancements could allow for timely warnings, providing operators and individuals the opportunity to brace for impact. It is a tantalizing prospect that merges the realms of science and human ingenuity, a testament to our desire to navigate the challenges presented by nature. In exploring the impacts of solar flares on communication systems, we are reminded that these cosmic events are not mere anomalies. They are integral to understanding our place within the universe. Each flare is a cosmic dialogue, urging us to listen and learn from the messages encoded in the waves of radiation that reach us. As we continue to innovate and adapt, we foster a future where our communication systems can withstand the solar storms that may come our way. The interplay between solar flares and communication technologies invites us to reflect on the broader implications of our relationship with the cosmos. Solar activity serves as a reminder of the power of nature and the necessity of resilience. In every disruption, there lies the potential for growth, innovation, and a deeper understanding of the universe that envelops us. As we face the unpredictable energy of the sun, we remain steadfast in our pursuit of knowledge and preparedness, ensuring that the connections we forge remain resilient against the backdrop of cosmic uncertainty. Chapter 7. Navigational Hazards, Aviation and Maritime Concerns. As we transition into the realm of aviation and maritime navigation, the shadow of solar activity looms large, particularly during solar flare events. These magnificent bursts of energy from the sun do more than just dazzle the night sky. They pose significant risks to aircraft soaring through the atmosphere. Imagine a pilot navigating a vessel of steel and technology when suddenly the sun releases a surge of energy. What happens next? The very fabric of communication and navigation can be disrupted, creating a challenging environment for those who depend on precise instruments and reliable signals. Solar flares release a cascade of electromagnetic radiation that can disrupt radio frequencies crucial for aviation. Pilots rely heavily on these frequencies for communication with air traffic control and for navigation. When a flare erupts, the intense electromagnetic pulse can create a phenomenon known as radio blackout, rendering these vital channels temporarily ineffective. It's a disconcerting thought to imagine being in a cockpit, surrounded by the vastness of the sky, yet unable to communicate or receive critical information. Furthermore, the risks extend beyond radio communications. Satellites, which play an integral role in navigation systems, can also be affected by the energetic particles emitted during solar flares. Imagine the delicate dance of satellites orbiting the Earth, each one a sentinel, providing invaluable data to aviators and mariners. When these satellites encounter the high-energy particles unleashed by a solar flare, they can experience malfunctions or even complete failures. This can lead to inaccurate positioning data, creating a significant risk for navigation systems that rely on global positioning system technology. Within the maritime domain, the implications of solar activity are equally profound. The tools that sailors depend on for accurate navigation, like compasses and GPS systems, can be thrown into disarray during high solar activity. The ionosphere, a layer of the atmosphere that reflects radio waves, can become charged with particles from solar flares, leading to disruptions in the signals that guide ships across the oceans. Imagine a ship navigating through fog, unsure of its precise location. This uncertainty can escalate into dangerous situations, especially in unfamiliar waters or during adverse weather conditions. To mitigate these risks, the aviation industry has developed safety protocols to follow during periods of heightened solar activity. Pilots and air traffic controllers are trained to be vigilant, monitoring solar forecasts and adjusting their operations accordingly. Imagine the calm yet focused demeanor of a flight crew preparing for a journey, equipped with knowledge of potential solar disruptions. They might change flight paths to avoid areas where navigation signals are likely to falter, ensuring that passengers remain safe and secure throughout their journey. Airlines often have contingency plans in place for solar storms, including rerouting flights in increasing altitude to avoid the most intense regions of solar radiation. The collaboration between scientists and aviation professionals is crucial. They work together to develop real-time monitoring systems that provide updates about solar activity. Pilots can receive alerts about significant solar events, allowing them to make informed decisions that prioritize safety. Historical instances of solar flares affecting navigation systems offer profound lessons. One notable case occurred during a solar storm in the early days of space exploration. A group of astronauts aboard a spacecraft found themselves navigating through a surge of high-energy particles. Communication systems faltered, and they faced challenges in maintaining accurate positioning. Yet, it was their training and preparation that allowed them to adapt and respond to the unexpected. This incident serves as a reminder of the resilience of human ingenuity in the face of cosmic forces. In another case, a commercial airline experienced a brief but intense radio blackout during a solar flare event. Pilots reported a sudden silence in their communications, an eerie stillness that enveloped the cockpit. Fortunately, the flight crew was well-trained and quickly adapted to the situation, relying on backup systems and their navigational skills to ensure a safe landing. Such incidents illustrate the importance of preparedness and the need for ongoing education about the potential impacts of solar activity on aviation. The maritime sector, too, has faced challenges posed by solar flares. There have been instances where ships found themselves adrift, their navigational systems rendered unreliable, due to the disruptions caused by solar activity. Without accurate data, even the most seasoned captain can feel adrift in a vast ocean. In response, the maritime community has begun to integrate solar activity forecasts into their navigation protocols. Sailors are now more aware of the potential for solar flares to impact their journeys and are taking proactive measures to ensure safety at sea. As we reflect on these navigational concerns, it is essential to appreciate the work of scientists who study the sun and its effects on Earth. Their research is vital for understanding the complexities of solar activity and its potential impacts on technology. It is through their dedication that we gain insights into the nuances of solar flares, allowing us to develop strategies that help protect aircraft and ships from the unpredictable forces of nature. In the face of these challenges, one cannot help but marvel at the resilience of those who navigate the skies and seas. They embody a spirit of adaptability, embracing the unknown while relying on their skills and training. As we continue to explore the intricate relationship between solar flares and navigational systems, we are reminded of the ever-present connection between humanity and the cosmos. Each flight taken and every voyage embarked upon is a testament to our unwavering quest for exploration, guided by the stars above and the mysteries of solar activity that lie beyond our reach. As we ponder the delicate balance between nature's forces and human innovation, we find ourselves at a crossroads of technology and the cosmos. The sun, a magnificent source of energy, continues to fascinate us, reminding us of our place within the universe. The challenges posed by solar flares serve not only as obstacles, but as opportunities for growth and understanding. Through continued research and collaboration, we can forge a path that enhances our ability to navigate both the skies and the seas, even in the face of solar uncertainty. As we look to the future, we can envision a world where science and human endeavor harmonize, creating safer skies and oceans for generations to come. What tales will emerge from our ongoing relationship with the sun? The journey of exploration continues, inviting us to ponder the mysteries that await us in the vastness of space and the challenges that lie ahead in our navigational pursuits. The risks posed to aircraft during solar flare events are multifaceted, extending beyond mere communication disruptions. One of the less visible yet significant effects is the potential for increased radiation exposure. High-energy particles emitted during solar flares can penetrate the atmosphere, resulting in elevated radiation levels at cruising altitudes. Imagine a passenger jet soaring through the clear blue sky, blissfully unaware of the cosmic forces at play. As it ascends to its cruising altitude, it enters a realm where the atmosphere is thinner, providing less protection against these energetic particles. Pilots are trained to be aware of these risks, particularly during periods of heightened solar activity. The Federal Aviation Administration and other regulatory bodies monitor solar activity and provide guidance on flight operations accordingly. When a major solar event is forecasted, airlines may adjust flight routes, opting for lower altitudes or altering paths to minimize exposure to radiation. These proactive measures protect not only the crew, but also the passengers, who may unknowingly be traversing through a potentially hazardous environment. What about the implications for long-duration flights, such as transpolar routes? These journeys, which often fly over the polar regions, expose aircraft to greater levels of solar radiation. The Earth's magnetic field is weaker at the poles, allowing more charged particles to enter the atmosphere. As such, pilots flying these routes must remain vigilant, continuously informed about solar activity that could affect their journey. Imagine the responsibility resting on their shoulders, guiding a vessel through a cosmic playground while ensuring the safety of all on board. In maritime navigation, the challenges brought forth by solar flares are equally profound. The potential disruptions to navigation systems can be likened to sailing through a thick fog, where familiar landmarks become obscured and reliance on technology becomes paramount. The Global Positioning System, a cornerstone of modern maritime navigation, can falter during solar events, leading to inaccuracies in positioning. This can have dire consequences, especially in busy shipping lanes or near coastlines where precision is critical. Consider the experience of a ship's captain navigating through a bustling port. Suddenly, the GPS system begins to falter, displaying erratic readings. The captain, trained to trust their instruments, now faces a critical decision. Should they rely on traditional navigation methods, such as celestial navigation or dead reckoning, to guide their vessel safely? Such moments underscore the importance of adaptability and training in the face of technological uncertainties. As we explore safety protocols for aviation during high solar activity, it becomes clear that preparation is key. The aviation industry has established guidelines and protocols designed to enhance safety during solar events. For instance, pilots may receive briefings on solar activity prior to flights, allowing them to anticipate potential disruptions. Flight crews are trained to maintain situational awareness and to communicate effectively, ensuring that they are well prepared to handle any unexpected challenges. One innovative approach has been the integration of real-time solar monitoring systems into aviation operations. These systems provide timely updates on solar activity, alerting pilots and air traffic controllers to significant events that may impact flight safety. Imagine the sense of security that comes from knowing that the skies are being monitored, that information is flowing seamlessly, and that every effort is being made to safeguard those in flight. In the maritime realm, the situation is evolving as well. The integration of solar forecasts into navigation protocols is becoming increasingly common. Sailors are now equipped with tools and knowledge that empower them to make informed decisions when navigating during periods of heightened solar activity. Imagine a seasoned sailor, once reliant solely on traditional navigation methods, now utilizing advanced technology to monitor solar flares and their potential effects on navigation systems. This combination of ancient wisdom and modern science creates a more robust approach to safety at sea. Historical case studies illuminate the realities of solar flare-related navigational incidents, revealing lessons that resonate through time. One notable instance involved a naval vessel operating in the Arctic Circle during a significant solar event. The ship's navigation systems began to malfunction, leading to confusion among the crew. However, they relied on their training and the experience of their captain, who had once navigated similar challenges. By employing traditional methods and working collaboratively, the crew successfully maneuvered through the treacherous waters, emerging from the incident with newfound respect for both their craft and the forces of nature. As we reflect on these stories, we are reminded of the indomitable spirit that resides within those who navigate the skies and seas. Their experiences highlight the importance of resilience and adaptability in the face of adversity. Just as the sun continues to shine above, illuminating our world, so too does the human spirit endure, seeking knowledge and understanding amid the uncertainties posed by solar activity. The study of solar flares and their effects on aviation and maritime navigation underscores the intricate connection between humanity and the cosmos. Each flare serves as a reminder of the dynamic forces at play, shaping our world in ways we are only beginning to comprehend. In our quest for exploration, we become not only observers of these celestial wonders, but also active participants in a larger narrative, one where science and the human experience intertwine. As we continue to delve into the relationship between solar activity and navigational systems, we must recognize that our understanding is ever evolving. Scientists, engineers, and navigators are united in their pursuit of knowledge, working collaboratively to enhance safety and resilience. What new discoveries await us on this journey? The answers lie in the fusion of curiosity and innovation, guiding us toward a future where we can navigate confidently, even in the face of solar uncertainties. With each advancement in technology and understanding, we strengthen our ability to traverse the skies and seas, embracing the wonders of our universe while honoring the forces that shape our existence. Chapter 8. Solar Flares and Power Grids. Energy Vulnerabilities. The sun, in all its brilliance, is a source of both wonder and vulnerability. When solar flares erupt, they unleash a torrent of energy that travels through the void of space, reaching Earth in mere moments. While these phenomena captivate our imagination, they also pose significant challenges to our modern electrical power systems. Imagine the sun as a giant, fiery beacon, capable of sending shockwaves across the solar system, and then consider the fragile web of wires and transformers that make up our power grid. What happens when this cosmic force meets the intricate machinery of our technology? As solar flares impact our atmosphere, they generate geomagnetic storms that can induce powerful electrical currents within the Earth's magnetic field. These currents can wreak havoc on electrical power systems, often manifesting as transformer damage. Picture a transformer, an essential component of our power infrastructure, as a delicate instrument designed to convert high-voltage electricity into a usable form. During geomagnetic storms, the induced currents can overwhelm these transformers, causing them to overheat and fail. The consequences of such failures can ripple through the grid, leading to power outages that can last for hours, days, or even longer. The historical record is dotted with instances where solar activity has disrupted our power systems. One notable event occurred in the early years of the 1980s when a powerful geomagnetic storm, triggered by a solar flare, led to widespread blackouts in Canada. The Hydro-Quebec power system was severely impacted as the induced currents damaged transformers and caused a catastrophic failure of the grid. This incident serves as a stark reminder of our vulnerability to the forces of nature. As Dr. Marcia McNutt once noted, the sun is a powerful force, and we must recognize its ability to disrupt our technological advances. Understanding these vulnerabilities is essential as we seek to protect our power grids from the unpredictable nature of solar flares. Various strategies have been developed to bolster the resilience of our electrical systems against these cosmic disturbances. One approach involves enhancing the monitoring and forecasting capabilities of solar activity. By using satellites equipped with sophisticated instruments, scientists can observe solar flares and predict their potential impact on Earth. Imagine a network of eyes in the sky, continuously watching for signs of solar activity, ready to warn us of impending geomagnetic storms. This proactive approach allows power companies to take precautionary measures, such as temporarily shutting down vulnerable transformers during intense solar events. Additionally, some utilities are investing in the development of more robust grid infrastructure, designed to withstand the effects of geomagnetic storms. This includes the installation of devices that can help mitigate the impact of induced currents, creating a buffer between the solar forces and our delicate electrical systems. Yet, as we fortify our grids, we also confront the question of how much we can truly protect ourselves from the sun's whims. The balance between technological advancement and natural forces is a delicate one. As solar flares continue to be a part of our celestial reality, we must remain vigilant and adaptable. The realm of power grids and solar flares is not without its challenges, but it is also a field rich with innovation and resilience. Engineers and scientists are continually exploring new technologies to enhance our ability to withstand these solar events. For instance, researchers are investigating advanced materials that can better resist the effects of geomagnetic storms, improving the longevity and reliability of transformers. Moreover, the integration of renewable energy sources into our power grids adds another layer of complexity. Solar energy, derived directly from the sun, offers a sustainable alternative to fossil fuels, yet it also requires careful management during periods of heightened solar activity. The duality of relying on solar energy while also being susceptible to solar flares highlights the intricate relationship between our technology and the natural world. As we ponder these challenges, it's fascinating to reflect on the historical instances where solar activity has affected our power systems. One particularly remarkable example occurred in the mid-19th century during a period known as the Carrington event. A massive solar flare erupted, sending a coronal mass ejection toward Earth. The resulting geomagnetic storm caused auroras to be visible as far south as the Caribbean and induced currents that disrupted telegraph systems across Europe and North America. The beauty of the auroras, however, masked the underlying chaos that ensued in communication and power systems of the time. This event serves as a poignant reminder of the intricate connection between the sun and our technological frameworks. It illustrates how, throughout history, the sun has shaped not only our natural world, but also the very fabric of civilization. As we continue to advance technologically, we must also acknowledge the potential vulnerabilities that come with our reliance on these systems. In light of these realities, it becomes increasingly important for communities and policymakers to prioritize preparedness for solar events. Public awareness campaigns can educate individuals and businesses about the potential impacts of solar flares on power systems and encourage proactive measures. Imagine a society where people are not only aware of the beauty of the night sky, but also understand the forces that shape their everyday lives. Embracing this knowledge can empower communities to take action, whether through investing in backup energy sources, encouraging energy conservation, or simply being informed about the nature of solar activity. The fusion of knowledge and preparation can create a stronger bond between humanity and the cosmos, allowing us to coexist with the magnificent forces of nature. As we move forward, the dialogue surrounding solar flares and energy vulnerabilities will continue to unfold. Advances in technology and our understanding of solar phenomena will undoubtedly lead to improved strategies for protecting our power grids. The landscape of energy production and distribution is evolving, and with it, the need for resilience against the unpredictable forces of the sun. In this intricate dance of energy and vulnerability, we find ourselves at a crossroads. The sun, with its magnificent power and beauty, invites us to reflect on our relationship with the cosmos. How will we harness its energy while safeguarding against its potential disruptions? The answers to these questions lie not only in our technological advances, but also in our willingness to adapt, learn, and prepare for whatever the sun may unleash upon us. The delicate balance of our power grids hinges on the intricate dance between solar activity and our technological infrastructure. As we delve deeper into the implications of solar flares, we find ourselves confronted with the reality of transformer damage during geomagnetic storms. These transformers, which play a pivotal role in converting and distributing electricity, are susceptible to the induced currents generated by the magnetic disturbances originating from solar events. When a geomagnetic storm occurs, the very foundation of these electrical giants can be shaken. The currents induced in the Earth's crust can create voltage surges that exceed the tolerances of these devices. Imagine a massive wave crashing against a fragile shoreline, each surge threatening to erode the stability of the land. This analogy reflects the tension between the forces of nature and the engineered systems designed to harness energy for our daily lives. The damage inflicted on transformers can lead to a cascade of failures, plunging entire regions into darkness and disrupting the fabric of modern society. Historical instances reveal the sobering truth of this vulnerability. The Quebec blackout serves as a chilling reminder of how a single solar event can lead to widespread chaos. Yet it is not the only incident that illustrates this point. In the mid-1980s, a series of geomagnetic storms caused disruptions to power systems across the United States, with transformers failing in several locations. Each event serves as a lesson, urging us to take proactive measures in safeguarding our infrastructure against the unpredictable whims of solar activity. To combat the potential devastation of solar flares, power companies are embracing innovative strategies to protect their grids. One such approach involves the installation of devices known as geomagnetic storm sensors. These sensors are strategically placed to monitor the magnetic field and detect disturbances in real time, providing invaluable data that can inform decision-making. By equipping power grids with advanced technology, energy providers can implement more effective measures to thwart the impacts of solar flares. Imagine a world where power companies can predict solar storms with remarkable accuracy, allowing them to protect the electrical systems that sustain our lives. This proactive stance enables utilities to take critical actions, such as temporarily reducing the load on transformers or rerouting electricity to less vulnerable areas. By anticipating the effects of solar flares, we can maintain a semblance of control in a world otherwise governed by cosmic forces. Yet, protecting our power infrastructure is not solely the responsibility of energy providers. Communities, too, play a vital role in this equation. Awareness and education are essential components of preparedness. Public campaigns can empower individuals to understand the potential impacts of solar flares on their daily lives, fostering a culture of resilience. Imagine a neighborhood equipped with knowledge, where residents know the importance of having backup generators and emergency supplies. Such preparedness can make a significant difference when the inevitable solar event occurs. As we continue to explore the relationship between solar flares and power systems, it is crucial to recognize the historical context that shapes our understanding. The Carrington event, one of the most significant solar storms recorded, serves as a pivotal reference point in this narrative. During this event, the eruption of a colossal solar flare sent waves of charged particles cascading toward Earth, leading to widespread disruptions in telegraph systems and even causing sparks and fires in some offices. This remarkable incident not only highlighted the vulnerabilities of the technology of the time, but also showcased the profound interaction between the sun and our communications networks. The reverberations of the Carrington event linger in the collective memory of scientists and engineers, guiding our efforts to bolster the resilience of modern technology. As we strive to fortify our power grids, we must also consider the interconnectedness of our technological systems. The age of the internet has ushered in a new era of reliance on digital communications, raising the stakes even higher. The potential for solar flares to disrupt not only power supplies but also communications and data networks underscores the need for a comprehensive approach to safeguarding our infrastructure. In the face of these challenges, innovative solutions continue to emerge. Research into advanced materials and designs for transformers is ongoing, with scientists exploring ways to enhance their resilience against geomagnetic storm impacts. These advancements hold promise for creating more robust and durable components that can withstand the forces of nature. As we ponder the implications of solar flares on our power systems, we are reminded of the dual nature of our relationship with the sun. While we harness its energy for light and warmth, we must also remain vigilant against its unpredictable behavior. The challenges posed by solar activity are not insurmountable. Rather, they inspire a spirit of innovation and adaptability. The quest for knowledge and preparedness is a journey that invites collaboration across disciplines, weaving together the expertise of engineers, scientists, and communities. As we forge ahead into an uncertain future, the lessons learned from history will serve as guiding stars, illuminating our path toward resilience. How we choose to respond to the sun's magnificent yet volatile nature will ultimately shape our technological landscape and the very fabric of our lives. In this ongoing dialogue with the cosmos, the interplay between solar flares and power grids invites us to reflect on our place in the universe. Each solar event is a reminder that we are part of a larger narrative, one that transcends the boundaries of our planet. As we face the challenges of tomorrow, let us embrace the power of knowledge and community, forging a future where we can coexist harmoniously with the forces of nature that shape our existence. Chapter 9. Monitoring Solar Flares, Tools and Techniques. As we explore the intricacies of monitoring solar flares, we find ourselves immersed in the realm of technology and human ingenuity. Satellite missions have become essential tools in our quest to understand and predict these powerful phenomena. Imagine a fleet of robotic eyes orbiting high above our planet, observing the sun with unparalleled precision. Each satellite is equipped with an array of instruments designed to capture the sun's energetic dance, allowing scientists to analyze the data in real time. One such mission is the Solar Dynamics Observatory, launched to relentlessly observe the sun's dynamic atmosphere. This satellite provides high-resolution images of solar flares across multiple wavelengths, enabling researchers to study the immediate effects of these explosions. Consider the breathtaking images of solar flares captured by the spacecraft, where bright flashes illuminate the sun's surface, revealing the chaotic interplay of magnetic fields. This mission not only aids in flare detection, but also helps us understand their underlying mechanisms. Another pivotal player in solar observation is the Solar and Heliospheric Observatory, a collaboration between NASA and the European Space Agency. This satellite has been continuously monitoring the sun since its launch, providing invaluable data on solar activity and its impact on space weather. Picture the wealth of information these missions have gathered, constructing a comprehensive picture of the sun's behavior over time. By analyzing this data, scientists can begin to piece together the patterns that precede solar flares, shedding light on their predictability. Ground-based observatories also play a crucial role in the monitoring of solar flares. These observatories are strategically located around the globe, equipped with powerful telescopes and instruments that complement the data gathered by satellites. Imagine standing in an expansive field, gazing through a massive telescope, as solar scientists observe the sun's surface for signs of activity. Facilities such as the Big Bear Solar Observatory and the McMath Pierce Solar Telescope focus on studying the sun's magnetic fields and sunspot formation, providing vital insights into the conditions that lead to flares. The collaboration between ground-based and satellite observations creates a robust framework for monitoring solar flares. By combining data from diverse sources, scientists can enhance the accuracy of their predictions. As they analyze the data collected, they utilize advanced algorithms and machine learning techniques to identify patterns and anomalies, transforming raw data into meaningful information. This process, much like piecing together a cosmic puzzle, helps to illuminate the intricate relationships between solar activity and the resulting impacts on Earth. Imagine the significance of this data collection and analysis. Each flare observed contributes to a growing reservoir of knowledge, allowing scientists to refine their models and improve prediction accuracy. In recent years, considerable advancements have been made in understanding the precursors to solar flares. Researchers have identified specific magnetic configurations associated with increased flare activity, providing a promising avenue for future predictions. As we look to the horizon of solar flare monitoring, emerging technologies hold the potential for even greater advancements. The next generation of satellites is poised to revolutionize our understanding of solar activity. For instance, future missions may incorporate advanced imaging techniques that allow for more detailed observations of the sun's surface and its magnetic field dynamics. Imagine a future where we can visualize the sun in astonishing detail, tracking the movements of plasma and magnetic fields with precision. Additionally, researchers are exploring the use of artificial intelligence to enhance predictive capabilities. Machine learning algorithms, trained on vast data sets from past solar activity, can identify patterns that human analysts might miss. Picture a system that learns from each solar event, continuously improving its predictions and enabling proactive measures to mitigate the impacts of solar flares on our technology and infrastructure. In the realm of ground-based observatories, advancements in technology are also promising to enhance our understanding of solar flares. Enhanced spectrometers and imaging systems will enable researchers to analyze the sun's emissions with greater accuracy. Imagine the ability to measure the electromagnetic spectrum of solar flares in real time, providing insights into their chemical composition and energy output. Each new piece of data feeds into the larger narrative of solar dynamics, guiding scientists toward a more profound comprehension of these captivating cosmic events. As we ponder the future, the integration of satellite data with ground-based observations, enhanced by artificial intelligence and advanced imaging techniques, paints a hopeful picture for solar flare monitoring. This synergy of technologies will not only improve our predictions, but also deepen our understanding of the sun's complex behavior. In this way, we can better prepare for the potential impacts of solar flares on our world, safeguarding our technological systems and enhancing our resilience against the forces of nature. The journey of monitoring solar flares is a testament to human curiosity and innovation. Each mission, each observation, contributes to a collective endeavor aimed at unraveling the mysteries of our closest star. As we continue to develop new tools and techniques, we move closer to mastering the art of solar observation, embracing the challenge of understanding the sun's magnificent power. What might we discover next in this quest for knowledge? The possibilities are as boundless as the cosmos itself. The exploration of solar activity has been enriched by the advancements in data collection methods. As scientists observe the sun, they rely on a variety of techniques to gather information about solar flares and their precursors. Imagine a vast network of sensors and instruments, each meticulously designed to capture the sun's behavior from different angles and wavelengths. This multifaceted approach enables researchers to build a comprehensive understanding of the processes driving solar flares. One of the most significant advancements in solar observation is the use of spectrometry. This technique allows scientists to analyze the light emitted from the sun in great detail, revealing essential information about its composition and the physical conditions present during a flare. When a solar flare erupts, it emits light across the electromagnetic spectrum, from radio waves to X-rays. By studying the spectrum of this light, scientists can infer the temperature, density, and velocity of the plasma involved in the flare. Imagine a rainbow, each color representing a different energy level, a spectrum that tells a story of the sun's tumultuous surface. The use of magnetographs is another crucial tool in this endeavor. These instruments measure the magnetic fields on the sun's surface, providing insights into the magnetic structures that give rise to solar flares. Understanding the magnetic environment is vital, as it is the twisting and tangling of magnetic field lines that often leads to the explosive release of energy. Picture these magnetic fields as invisible threads weaving through the sun's atmosphere, their intricate patterns crucial to predicting when and where a flare might occur. Data from satellite missions like the Solar Dynamics Observatory and the Solar and Heliospheric Observatory is complemented by ground-based observations. Ground-based observatories, such as the National Solar Observatory in New Mexico, employ advanced imaging and spectroscopic techniques to monitor solar activity continuously. These facilities contribute to a global network of solar observations, where data can be shared and analyzed collaboratively. Imagine a symphony of scientists across the world, each contributing their unique observations, harmonizing their findings to gain a clearer picture of solar behavior. The analysis of solar data is not merely a matter of observation. It involves sophisticated computational techniques and theoretical modeling. Scientists employ numerical models to simulate the sun's behavior, testing hypotheses about solar dynamics and flare prediction. These models take into account various factors, such as magnetic field configurations and plasma dynamics, allowing researchers to explore scenarios that might lead to solar flares. As the models evolve, they help refine our understanding of solar phenomena, much like a sculptor chiseling away at a block of marble to reveal a masterpiece hidden within. The intricate dance of data analysis and theoretical modeling has led to significant breakthroughs in understanding solar flares. Researchers have identified specific magnetic configurations that are prone to flares, such as the emergence of magnetic flux ropes or the presence of active regions on the sun's surface. These findings are akin to uncovering the fingerprints of solar activity, providing clues about the conditions that foster explosive events. As we look forward, the future of solar flare prediction is poised for transformation thanks to the integration of machine learning. This innovative approach leverages vast amounts of historical data, enabling algorithms to identify patterns and anomalies that may signal impending flares. Imagine a system that learns from every solar event, continuously improving its predictive capabilities. Such advancements could allow for timely warnings, safeguarding technologies and human activities from the disruptive effects of solar flares. Moreover, future satellite missions are expected to incorporate even more advanced technologies. The next generation of solar observatories may utilize high-resolution imaging combined with real-time data processing capabilities. This would enable scientists to visualize solar flares and their precursors in unprecedented detail. Picture the sun's surface coming alive in vibrant colors, revealing the hidden dynamics of solar activity as never before. In addition to these technological advancements, international collaboration will play a crucial role in the future of solar monitoring. As the sun does not respect national boundaries, a concerted global effort will enhance our understanding and predictive abilities. With the establishment of networks that share data and insights, scientists can work together to unravel the complexities of solar activity. Imagine a community of researchers from diverse backgrounds, cultures, and expertise uniting in their quest to understand the sun, each contributing their unique perspectives to a shared goal. As we ponder the implications of these advancements, we recognize that the study of solar flares is not merely a scientific pursuit, it is a testament to human curiosity and resilience. Each discovery propels us closer to mastering the art of solar observation and prediction. What mysteries might we unveil as we continue on this journey? The sun remains a powerful force, its secrets waiting to be discovered, inviting us to look up at the sky with wonder and awe. As we immerse ourselves in the intricate web of solar observation, we encounter a rich landscape of methodical advancements in data collection and analysis. These techniques are fundamental in capturing the sun's elusive behavior, particularly its explosive solar flares. Imagine a vast array of instruments, each meticulously positioned to observe different aspects of the sun, akin to the strings of an orchestra, all contributing to a harmonious understanding of solar dynamics. One of the most promising methods currently being developed is the use of imaging spectroscopy. This technique combines imaging and spectroscopic data, providing a multi-dimensional view of solar flares. By capturing images at various wavelengths simultaneously, researchers can gain insights into the temperature, density, and motion of solar material. Picture this as not merely viewing a photograph, but rather peeling back layers of a cosmic onion, revealing the complex interplay of forces at work during a flare. Furthermore, the evolution of data processing techniques plays a vital role in enhancing the analysis of solar activity. High-performance computing has transformed the ability to process vast quantities of data generated by solar observatories. With the sun's activity producing immense data sets, employing sophisticated algorithms allows scientists to sift through and extract meaningful patterns. Imagine a treasure hunter, meticulously searching through a mountain of sand to uncover precious gems. The gems in this case being the insights that can lead to better predictions of solar flares. The integration of machine learning and artificial intelligence into data analysis signifies a paradigm shift in solar research. By training algorithms on historical flare data, scientists can identify subtle indicators that might precede a solar flare. This predictive modeling not only enhances our understanding of flare dynamics, but also contributes to the development of real-time alert systems. Imagine a world where, with a few clicks, we can be alerted to an impending solar event, allowing us to take precautionary measures to safeguard vital infrastructure. As we contemplate the future of solar flare prediction, the potential of satellite constellations becomes apparent. Future missions may involve a network of satellites working in tandem, each equipped with specialized instruments to monitor the sun from different vantage points. This collaborative approach could yield a multifaceted view of solar activity, akin to a multi-camera setup capturing a grand performance from various angles. The synergy of this data could drastically improve our predictive capabilities, enabling us to forecast flare occurrences with greater precision. Moreover, as solar flares can significantly impact Earth's magnetosphere, future technologies will likely focus on real-time monitoring of these interactions. Imagine a system that not only predicts solar flares, but also assesses their potential effects on Earth's magnetic field and atmosphere. This holistic approach to monitoring could act as a safeguard, providing timely warnings to protect our technological systems from the disruptive forces of solar activity. In this journey towards enhanced solar flare monitoring, the international collaboration of researchers and institutions stands as a beacon of hope. By pooling resources and knowledge, scientists from around the globe can share data and insights, fostering a deeper understanding of solar phenomena. Picture a global network where researchers communicate seamlessly, their collective wisdom guiding us toward a future where solar flares can be anticipated with confidence and clarity. As we continue to explore these advancements, we recognize that the study of solar flares is not just a scientific endeavor. It is an ongoing quest to understand the sun's profound influence on our lives. Each breakthrough in technology and methodology brings us closer to unveiling the mysteries of our nearest star. What lies ahead in this ever-evolving landscape? The anticipation of discovery fuels our curiosity, inviting us to gaze into the cosmos and ponder the wonders that await us. Chapter 10. Preparing for Solar Flares, Awareness and Safety. As we stand on the brink of a new era of understanding solar flares, the importance of public awareness cannot be overstated. Imagine a world where communities are educated about the sun's behavior, where individuals understand the potential impacts of solar flares on their daily lives. This awareness is not merely an abstract concept. It is a vital strategy for mitigating the risks posed by these cosmic phenomena. Engaging the public through educational campaigns, workshops, and accessible information can empower individuals to recognize the signs of solar activity and comprehend its implications for technology and safety. Consider the role of social media and digital platforms in this age of communication. These tools can serve as lifelines, transmitting timely information about solar events to a broad audience. In moments of heightened solar activity, alerts can be disseminated rapidly, informing the public about possible disruptions in power or communication systems. The key lies in fostering a culture of preparedness, where individuals are not left in the dark, but rather equipped with knowledge and resources to respond effectively to solar flares. In the face of potential communication disruptions caused by these solar events, developing contingency plans becomes paramount. Imagine the tranquility of knowing that, should a solar flare disrupt communication systems, you have a backup plan in place. This foresight can be as simple as ensuring that family members know how to reach each other through alternative means, or as complex as communities establishing local networks to share information during such events. The historical record of solar flares teaches us about the vulnerabilities in our communication infrastructure. The Carrington event serves as a poignant reminder of how profoundly a solar flare can impact the Earth. In this incident, telegraph systems across North America and Europe experienced widespread failures, illustrating the fragility of our technological networks. The lesson here is clear. We must prepare for the possibility of future solar flares with robust contingency plans. The importance of research and funding for solar studies cannot be overlooked. As we strive to enhance our understanding of the sun, the need for sustained investment in solar research becomes increasingly vital. Imagine a future where scientists have the tools to predict solar flares with remarkable accuracy, where communities can be alerted in advance to mitigate disruptions. This vision is achievable through dedicated funding for research initiatives, supporting institutions that focus on solar studies and the broader field of space weather. The work of outstanding researchers in this field has led to significant advancements in our understanding of solar activity. For example, the development of advanced computational models allows scientists to simulate the sun's behavior and predict potential flare activity. These innovations are crucial for enhancing our preparedness and response capabilities. As one prominent solar physicist noted, Understanding the sun is a journey, not a destination. This journey requires ongoing commitment and collaboration across various disciplines. Encouraging community preparedness for solar weather events is a collective responsibility. Picture neighborhoods coming together, sharing knowledge and resources, and creating plans that address the unique challenges posed by solar flares. This could involve organizing community drills to prepare for potential disruptions, ensuring that emergency kits include essential items for communication and power outages. Engaging local leaders and organizations in these efforts can amplify the message of preparedness. Schools, civic groups, and local businesses can all play a role in spreading awareness and fostering a culture of readiness. Imagine a community where solar weather events are discussed openly, where citizens feel empowered to take action and safeguard themselves against potential disruptions. In this interconnected age, partnerships between government agencies, educational institutions, and private sectors can bolster our response to solar flares. Collaborative efforts can lead to the creation of comprehensive resources, ensuring that individuals have access to accurate and timely information. Imagine a web of support where knowledge flows seamlessly among various sectors, creating a well-informed populace ready to face the challenges posed by solar flares. The impacts of solar flares extend beyond immediate disruptions. They also carry long-term implications for our technological infrastructure. As we deepen our understanding of these phenomena, it becomes crucial to consider how we can fortify our systems against their effects. Investing in resilient technologies and infrastructure can help safeguard against the potentially devastating consequences of solar activity. Furthermore, ongoing research into the effects of solar flares on power grids and communication systems can illuminate pathways to enhance our resilience. By understanding the mechanisms through which solar flares affect our technology, we can develop strategies to mitigate these impacts. Consider the advancements in materials science that could lead to the creation of more resilient power transformers, designed to withstand the induced currents from geomagnetic storms. As we prepare for the future, it is essential to maintain an open dialogue about solar activity and its implications. Community forums, educational presentations, and public discussions can serve as platforms for sharing knowledge and addressing concerns. Imagine a space where individuals can voice their questions and fears, creating a supportive environment that fosters understanding and preparedness. In this context, we must also recognize the importance of international cooperation in monitoring solar activity. Solar flares do not recognize borders. Their effects can ripple across the globe. Collaborative efforts among nations can enhance our collective understanding and response capabilities. Sharing data and resources allows for more comprehensive monitoring and analysis of solar phenomena, leading to improved predictions and preparedness strategies. The sun, in all its complexity, continues to be a source of wonder and challenges. As we look ahead, let us embrace the responsibility of preparing for solar flares with a spirit of collaboration, awareness, and resilience. With each passing day, we inch closer to a future where communities are not only informed, but empowered, ready to face whatever the sun may bring. The journey of understanding and preparing for solar flares is just beginning, and it is a journey we must embark on together. As the sun continues to illuminate our days, the importance of public awareness strategies for solar flare impacts becomes increasingly evident. Communities must be equipped with the knowledge necessary to understand not only the phenomena themselves, but also the potential ramifications for their daily lives. Imagine a community where the local library hosts workshops educating citizens about solar flares, their causes and effects. In these sessions, participants engage in discussions about preparedness and learn to recognize the signs of increased solar activity, evolving from passive observers into informed advocates for their own safety. The power of storytelling can be harnessed to create a narrative around solar flares that resonates with individuals' experiences. By sharing personal accounts of how solar flares have affected technology, From disrupted phone signals to unexpected power outages, communities can foster a deeper understanding and connection to the subject. This grassroots approach serves not only to inform, but also to unify members of the community around a common goal: preparedness. In addition to storytelling, incorporating visual aids and interactive elements can enhance comprehension. Imagine creating a vibrant display that illustrates the sun's layers and the mechanisms that lead to solar flares. Such an exhibit could transform abstract scientific concepts into tangible experiences, inviting visitors to explore the sun's power and its potential effects on Earth. Engaging visuals and hands-on activities can ignite curiosity and inspire individuals to seek further knowledge. As we develop contingency plans for communication disruptions, it is crucial to establish clear protocols that everyone can follow. Envision a scenario where a solar flare disrupts cellular networks, leaving people without their usual means of communication. Having a well-defined plan in place, such as designated meeting points or alternative communication channels, can alleviate anxiety and ensure that families can reconnect amidst chaos. Communities can also benefit from creating a network of volunteers trained in crisis communication. Imagine individuals equipped with walkie-talkies, ready to relay information and assist those in need during solar weather events. This proactive approach not only fosters resilience, but also strengthens community bonds, as neighbors come together to support one another during challenging times. In this digital age, the role of technology in our preparedness strategies cannot be understated. The development of mobile applications dedicated to solar weather alerts can play a vital role in keeping communities informed. Imagine receiving a notification on your smartphone alerting you to an impending solar flare and its potential impacts. These applications can provide real-time updates, guidance on safety measures, and even educational resources about solar activity. The significance of research and funding for solar studies cannot be emphasized enough. As we invest in our understanding of solar phenomena, we pave the way for advancements that can enhance our preparedness and response capabilities. Consider the potential breakthroughs that could arise from increased funding for solar research institutions. A collaborative effort among scientists could lead to the development of new predictive models, enabling better forecasting of solar events and their likely impacts. The work of pioneering researchers has laid the foundation for our current understanding of solar flares, but there is still much to be explored. The contributions of scientists like Lika Guhathakurta, who have dedicated their careers to studying the sun, highlight the importance of nurturing a new generation of solar physicists. By inspiring young minds to pursue careers in solar research, we can ensure a continued focus on understanding these celestial phenomena. Encouraging community preparedness for solar weather events requires a multifaceted approach. Imagine local schools integrating solar science into their curricula, teaching students about the sun's behavior and the importance of preparedness. By instilling this knowledge in the younger generation, we equip them with the tools to advocate for themselves and their families in the face of solar flares. Furthermore, community preparedness can extend beyond education and into simulations and drills. Picture a neighborhood organizing a drill to practice their response to a solar-induced communications blackout. Such exercises can prepare individuals for real-life scenarios, transforming uncertainty into confidence. The shared experience of preparing for solar events strengthens community ties and fosters a collective sense of responsibility. The importance of collaboration between various sectors cannot be overstated. Public-private partnerships can enhance our response capabilities by pooling resources and expertise. Imagine technology companies collaborating with government agencies to develop innovative solutions for mitigating the impacts of solar flares on infrastructure. Such partnerships can lead to the creation of resilient technologies designed to withstand solar activity, safeguarding our essential services. In fostering a culture of preparedness, we must also prioritize inclusivity. It is crucial to ensure that all community members, regardless of background or circumstance, have access to information and resources related to solar flares. Consider the impact of multilingual outreach programs that cater to diverse populations, ensuring that no one is left behind in the quest for safety and knowledge. As we contemplate the future, the interplay between research, technology, and community engagement becomes clear. Imagine a world where solar flares are no longer a source of fear, but a phenomenon that we understand and can prepare for collectively. By investing in research, fostering public awareness, and cultivating community preparedness, we can build a resilient society, one equipped to face the challenges that solar flares may bring. Through these efforts, we can strive for a future where the impacts of solar flares are minimized, where communication systems remain intact, and where communities thrive in the face of cosmic events. The journey toward preparedness is ongoing, but with each step we take, we move closer to a state of readiness that empowers us to embrace the sun's magnificence while safeguarding our way of life.